Okay, so we are ready to start looking at module number 5. You're going to notice that module number 5 is going to be about belt and chain drives. So we're going to look first at our learning plan. So the learning plan that we have here, oh, I forgot to get rid of this. I'm so sorry. I'll get rid of this. This was a copy and paste from chapter 10, and I guess I forgot to take the lecture out. This is not your lecture. I'm going to be recording that right now, so that will repopulate in here. But you'll notice starting here, right at number 1 here, it says read chapter 11, and then we're going to be going through the PowerPoint here. So if you want to click on that, that's going to be a PDF of the PowerPoint for chapter 11 for the sections that you'll be responsible for that'll pertain to the homework or the homework assignment that we have. We will look at the homework assignment, but we'll wait for that until after we're kind of done going through things. So I'm going to pull up our chapter 11. Zoom out here a little bit, and we're going to use this PowerPoint to guide us through the chapter. So if you want to open up your book to page 302, as the figures come up, we'll be looking underneath my camera here, but we'll get started on our PowerPoint presentation. So the objectives of this chapter are going to be, number 1, to describe the advantages of belt drives. We're also going to be looking at identifying several different types of belt drives, but really focusing on one particular, and that's just going to be the run-of-the-mill V-belt drive as far as designing for. We're going to analyze the kinematic relationships of the 2 shafts that are coupled by a belt drive, and then we're going to do this very same thing for chain drives. Chain drives and belt drives, they go together really nicely because they're very similar in nature as far as the kinematics. The means to do the same type of a job is different, but we're going to see a lot of similarities actually also from what we did in gears. So that's what we're going to be focusing on here today. So belts and chain drives are used to transfer power between rotating shafts. This is the same job that gears had, okay? Belts and drives offer some extra flexibility, though, to what gears can. And that's going to be in being able to have more of a adjustable or a wider range of center distances that they can accommodate. When we have gears, they have to be right up against each other, and they don't have that ability to kind of be more flexible and move center distance wise, where sometimes we need that for the machinery that we're working on. So gears sometimes become impractical when we're trying to span especially large distances with shafts. So a bicycle chain drive is going to be a good practical example that I'm sure most of you all have experience with, or if all of us do. So the train mechanism is going to transfer the motion and the forces of the rotating gear assembly from that where you have the pedals to the rear wheel, which is going to be doing, if you would, the driving. The velocity ratio of that chain can be readily altered by relocating that chain. So on the gear shifter that you have on your bike, for instance, on a 10 speed, 12 speed, 20 speed, however many speeds are on your bike, you have the levers that are then going to push that chain from one to the next, type of sprocket that's going to be on the drive. Changing the velocities, if this would be a gear drive, is a lot more complex, and it's kind of like hardwired in. So it's going to require more hardware, which is impractical for a bicycle. And so a chain drive adds that flexibility that's needed, as well as being lightweight and relatively low cost. Now, belts and chain drives are a lot of times referred to as flexible connectors, and belt and chain drive kinematics are going to be exactly the same. So that's what's nice about kind of clustering these together, because we're going to see a lot of the same, formulas, if you would, come up. So again, we're going to focus first in the first part of this chapter on belts, and then we're going to be moving over to chains. We're on chapter 11 in our book. So the function of these belt drives is going to be to transmit that rotational motion and torque from one shaft to another, but in a smooth, quiet, and inexpensive way. Okay, so some advantages of belt drives that are characteristic of why we would maybe want to incorporate them into a design are going to be, first of all, they're pretty low cost. Okay. When we look at belt drives, we're gonna be looking at some of the basic types in here. They're gonna be ones that are gonna be familiar to you. Okay. They're also going to be flexible on that center distance. As I said earlier, when we have gears, those gears have to be in those spots and they have to stay there in order to do the transmitting. On the other hand, when we have belt drives and or chain drives, we have that flexibility of getting further apart or closer together as needed, depending on the application. They also operate smoothly and quietly by the nature of the materials that they're made of. Okay. Gears can sometimes be kind of loud because it's metal on metal that's coming around as those teeth engage and disengage. When we have belts, there isn't going to be any lubrication required. Okay. This is kind of huge. All right. Chains and gears require lubrication so that over time, they don't immaturely wear out. And it also dissipates heat and also that metal to metal contact that occurs. Belts are different. They don't require that. They're easy to assemble and install. They have very little maintenance. And then usually by the time you need to replace them, it's been, quite some time, and you can like visually see that it's time because of maybe fraying that's occurring on that belt. They also are good at absorbing, for instance, a shock load. So if you have a sudden overload, they can usually take it without really damaging, their hardware, if you would. Now, materials that belts are made out of. I was expecting this to look just a little bit different, but that's okay. So materials that we're going to have our belts made out of are going to be rubberized fabric, rubberized cord, reinforced plastics, leather, fabric, and combinations of the sorts. Sometimes they even have like metal cord or wire running through them to create some additional strength and such. If we look at different types of belts, we're going to go to the top of page 303 underneath. And right at the top here are a number of different types that are popular for industrial types of applications. So we've got a flat belt, V-belt. Now the V-belt is what is the most popular type of a belt. And we are going to be looking at sizing exactly this type. Even though we're not looking at these other ones in application in this chapter, the very same process would hold, except you would just use the manufacturer's data to kind of walk through the very same thing to get the same information. So here's your V-belt drive. You can also have them kind of ganged together. So you can have multiple V-belts. And what this offers is going to be more friction as it actually runs. Then we've got the cogged type. Now the cogged type have these little like half rounds in there, but they are not for catching, for instance, a tooth or something on a shiv or a pulley. What it does is it offers flexibility so that it can be actually gone around smaller radiuses. And then lastly, we have the timing belt kind. The timing belt kind does have a tooth shiv that it's actually going to be working with. Now, as we look at the V-belt, you're going to notice that we have this cross section coming down here. That cross section is going to snug and fit down in a groove on what we call a shiv or a pulley, S-H-E-A-V-E, okay? So that shiv has the same profile on it, and it's going to accommodate whatever type of a shape of a V-belt that we have. So what you need to do is you need to match up the belt profile to the actual shiv itself. So you have to have those are going to be mating. Okay. You can't use, different configurations of belts on different shivs. All right. They have to be matched up. So this V is going to accommodate that. Now you'll notice here that our shiv has a pitch diameter. That pitch diameter is going to kind of be like a gear tooth, if you would, and it's going to match up with, on our V belt, for instance, where we have kind of the strongest portion going through here. You'll notice that they have those little dots in there. That is going to be some type of material, whether it's steel or it can be a lot of different things, but it's going to be the strength area of that V-belt or the effective diameter. So a portion of this belt is going to stick out just above the shiv, but then the rest of it is going to rest down in and snug down in to that V. Now, what holds the belt in place is going to be friction, okay? So the sides, I'm going to go back up here again. The sides of these, as it runs, actually snugs down in there, all right? And by design, they are going to be able to transmit a certain amount of torque, okay, and or force. But if it gets overloaded, they start to slip, which is usually an advantage, because what it does is it protects any really expensive equipment. So that if there is an overload or a jam or something sudden happens that wasn't expected, the belt starts to slip, okay? And that's good, because again, it's going to protect some like downstream types of machinery that could be very costly to replace or repair. Now, as we look to the right here, you're going to notice that these have the same profile, but we've got them ganged up where there's multiples. This offers more surface area for friction. Okay, so what that means is that you're going to have the ability to then run higher torques, higher horsepowers through belts that have more cross-sectional area. Okay, but again, they offer that very same thing where they're going to work, you know, actively within the operating, you know, RPMs and torque that you have, but they will slip when they get overloaded. Okay. As we look down here, it's worth mentioning the timing belt sort. The timing belt sort is going to have to fit onto, and it's really kind of like kind of a gear matching up with another gear. So the space in between here is going to accommodate teeth on another type of sheave that is going to be specific to the timing belt that we pick out. So it kind of combines, if you would, the positive nature of a gear, but the flexibility of a belt and the quietness of a belt. Right. All right, let's catch up in our PowerPoint, because I know I went probably a little bit further along. So we've got the types. Materials we talked about. Oh, see, I think I just didn't get that out of there. That was the one I was expecting. So if we look specifically at sheaves, and we mentioned some of these things already, it's a wheel that is going to be connected to the shaft, and it's going to carry the belt. So that belt profile has to match whatever the groove in that sheave is. So that was that figure that we just looked at. They're classified by their pitch diameter. So if we look at table 11.1, and that is on that very same page, on page 306, you're going to notice here that there are 1, 2, 3 columns that are associated with kind of a family of belts, okay? And in each one of these, they're listing the standard sheave pitch diameter. So again, the pitch diameter is going to be that what we call effective diameter. So it's not the very top of the sheave, it's not at the bottom or the root, it's in between there, okay? So that's going to be our pitch diameter, and these are going to be the standard sizes that are going to be commercially available for us. When you're going to be doing your homework problems and the examples that we do to reinforce this and kind of walk through the process, we are going to only be looking to sheaves that are on this list. We are not going to be like willy-nilly, you know, picking them out of the air. The better place, or the more complete list, is when you're out in industry and you have a vendor that you're targeting to buy your V-belts and pulleys from, because these will be purchased parts that you incorporate into your designs. This isn't something you're going to make. All right. There are vendors that do this and make a ton of them. And what you need to do then is work off of their list. They'll make all of these and these standard sizes of 3V, 5V, and 8V belts. Those are like 3 popular categories. And then the ones that are listed here, again, are part of a standard. So if you're saying I'm a V-belt manufacturer for this profile, then you're going to be making these, but you may make extra ones, maybe some that are, you know, going to expand your offering, but they're not going to be listed as a standard. Additionally, the process that we're going to be going through here is going to be the books process. If something is different for a manufacturer, you want to always be looking to their process for incorporating into your design, so that if there is a warranty issue that you need to go back to them for, they're going to ask you, how did you size it? How did you put it in? Did you use our recommendations? And then you'll have to prove that, for instance. And so you want to always be looking to their process, even though this is a good guide and these are going to hit the high points. A certain manufacturer might have some nuances that they want to be sure that you do as you incorporate. Now, as far as these 3 different size belts, you're going to notice just below that there's a nice picture of what they physically look at, like, and what the dimensions would be. So you'll notice that our 3V belt is going to be the smallest, then there's the 5V, and then the 8V. So as you can imagine, as you get larger, you're going to be able to push higher horsepowers and torques through the larger belts. Okay, and again, you can do multiples of these if needed, if you need the extra friction for pushing higher values through. Now, V-belts themselves, the industrial V-belt selection chart is going to be based on the horsepower and the RPM. Okay, and then also the application. So if we go to page 304 in your book, at the very top, you're going to notice the chart that we see right here. Okay, now on this chart is for industrial V-belt selection. Along the x-axis is going to be what we call our design horsepower. And then we're going to have our RPMs of our faster shaft. Okay, so in the instance of gears, we call that pinions. Okay, in here we either call it a driver or a driven sheave or pulley, okay, for a V-belt. So a driver is going to be the faster of the two. The driven is going to be the slower of the two. So if it's a direct application, for instance, where we're coming right off of a motor and we're going to be, you know, attaching to, I think a little bit later, we're looking at some sort of a mixer, I think, an industrial mixer, or this one's a grinding wheel. So when we look there, we're going directly from the motor to our grinding wheel. Okay, so the driver would be off of the motor, the faster moving or RPM, and then the driven is going to be the one that's going to be on the grinding wheel. Okay, so this is going to be of the faster shaft or from the driver. All right, now when they talk design horsepower, and this is in kinematics, you have to remember, we go back to the very beginning of kinematics. We're not interested in so much what are the forces that are present. But when we talk design horsepower, we are going to be taking into consideration the volatility of the actual operation. And in this book, they don't consider that. So when they tell you what a motor RPM is, for instance, if it's 50 horsepower, you're just going to read 50. Many times, and when we get to design of machine elements next term, we're going to know more about the application, and we're going to categorize it as such, how volatile it is, what is the chance of overloads. So for instance, if it's if we're doing a belt drive for an automobile as opposed to a belt drive for a rock crusher in a quarry, they're going to have very different design horsepowers that we're going to deal with. An automobile is going to be closer to the actual horsepower of whatever it's coming off of, but a rock crusher in a quarry is going to have a higher factor that we're going to be taking into consideration. So its design horsepower will be higher because we're expecting, more overloads to occur. So that we're going to beef up our application as such. So design horsepower here for kinematics, we're going to read directly from what the horsepower is coming off of our driver or our motor. Okay, and assume that that's going to be the same for everything. Okay. Now, as we look here, we're gonna line up our design horsepower with our RPM of our faster shaft, and where those two come together in whatever section this is a good place to start with your design of your belt and what size we're actually going to go with. Okay, and that's how we're going to use this. It gives us guidance of, rather than picking it out of the air. As it says here, it's always best to consult with your actual manufacturer's catalog or sizing data, because then you are working off of their actual data, so that if there is an issue with the application, or if it for some reason fails earlier than you thought, you can always go back to that and see if there's any warranty that they can work with you on. So as we look at the actual belt drive geometry itself, at the bottom of page 304, we're going to be looking at figure 11.5. So let's take a peek over there. And we're going to look right down at this illustration here. So this is going to be a very typical, like entry level, if you would, belt drive, where we've got a smaller sheave, a larger shiv. So the smaller one most often is going to be our faster moving shiv. Doesn't have to be, but probably 98% of the time it's going to be. So this would be coming off of our motor. And then we are going to be having it engaged with our driven shiv over here, which is going to be larger to slow that speed down, increase the torque, and so that it becomes usable for whatever machine we're looking at. Now, just like with a gear, we can train these together. So right now, between these two, this would be considered a velocity ratio. They're not touching each other like gears did. They're just further apart, but based on their diameters, their sizes of the pitch diameter of the driver and the pitch diameter of the driven, we can compare those two sizes and come up with the very same velocity ratio equation that we were using for gears before. Okay, but now we just have the flexibility of moving them apart or closer together based on whatever center distance that we need. Now, a couple other things. You're going to notice here that they call this a tight side and a slack side. Based on the direction of the driver, it's pulling this belt around. So this is going to be the side that it's pulling on. So it is going to be the tight side. And then the slack side is going to be exactly that. There's not going to be as much tension on that side. And what can happen is this slack side, if you get too far apart with it or too close, you can have problems with this creating extra vibration, which you don't want to have. So in here, they do give us a range for a optimally size center distance. Okay, so capital C here is going to be the center distance between our driver and our driven. And to get the range that we want to go within, we are going to use this, I guess it's sort of an equation, not really an equation that we're solving for something, but we want to check, we want to make sure that whatever center distance we come up with or need is going to be greater than the diameter of the driver. So kind of between there, and 3 times whatever the pitch diameter of the driven and the driver together is going to be. Okay, so the center distance has to fall between those two numbers, and that's going to be a large range. So, but you just want to always check to make sure that it's in there, and that's part of the process that you're going to be looking at. Okay. Now, the next equation that we see down here is going to be the length of the belt. Okay, the length of the belt is going to be determined by knowing the center distance and the diameters of each one of the shifts. Okay, now the belt for a V belt is always going to be continuous. Okay, so what you have to do is in your design, and although in kinematics we're not accounting for that right now, you will later on in machine design when we kind of finish things up, but you have to be able to push one of these shifts in and out in order to, number one, be able to, as you push one of these in, I'm just going to use the motor for right now, or the driver for right now. If you push it in, you have to have the ability to take that V belt and go over the top of each one of those shifts and then push it back to snug it back up so that it's nice and tight, okay, for operating. And then if you ever need to, you want to also build in what they call take up, because over time, those belts are going to stretch out. Okay, so you have to build that into your design as well. And then lastly, you have to have the ability to take it off. Okay, it's a continuous belt, so you have to have that ability to move in and out in order to accommodate for install and then also take up and then also taking off. So your length of your belt is going to be determined on those. And then here's our center distance. And then the last part of this is angle of twist, or I'm sorry, I said angle of twist, angle of contact. Your angle of contact is going to be how much of that belt on each one of my shifts is actually going to be on the circumference. Okay, how much of that? And there is going to be a minimum amount that you need, and that is going to be here at 180 degrees. So you need at least 180 degrees of wrap, if you would, of that belt on both of these shifts. So notice that it's a little bit over 180 on this side and a little bit over 180 on that side. It avoids allowing these to get too close. Okay, and then we have the range for the center distance so that they don't get too far apart as well. okay? Belt isn't as quite of a problem with further apart and sag as a chain drive would be, okay? A chain drive will sag because of just the weight of it compared to a belt. It's a belt is going to be a lot less heavy. So we talked about belt length calculations, and the calculations will make a little bit more sense, and the center distance as well as the angles of contact when we do an example that will be calculating each one of these. So it's just a place that you know where we're going to be finding those in our book. Now, let's talk about velocity ratio. So velocity ratio is going to look and sound very familiar to us. So we've already experienced and defined and calculated velocity ratios as we looked at gears, okay? The very same thing occurs here, except when we're talking belt, like a V-belt, we don't have teeth to count, okay? If you had a timing belt, you could count teeth, okay? But we're just going to be working with the smooth V-belts. So the dimensions that we have to work with are going to be the rotational speeds of our driver, which is going to be W1, and our driven, which is going to be W2. So our higher speed is going to be the W1. And then as we look to the right, we can compare then the pitch diameter of the larger sheave, which is going to be the driven, divided by the pitch diameter of the smaller sheave, which is going to be the driver. Okay, larger number you always want on top. All right, and the smaller number on the bottom. And then these are just the radiuses of those. So most often we're interested in those diameters because that's how we're going to size our sheaves or call them out rather than on a radius. But the radiuses are here for us to work with as well. All right. Now, another consideration here is that belts are going to transfer their maximum power at speeds between 4,000 and 5,000 feet per minute, okay? And this is going to relate to the speed of the belt, the linear speed of the belt, okay? Remember in gears when we talked about pitch line speed, very same thing here. So if we look at equation 11.8, which is on page 306, right at the top here, this is pitch line speed. It's that straight line velocity component, and it's going to be equal to the radius of our sheave times how fast it's going around, the rotational speed. But remember that this has to be in radians per second or radians per minute, whatever we're dealing with in terms of your unit of time. But you cannot put RPMs in for that W, just like we couldn't for gears. Okay, so this is your, if you would, pitch line speed, or in this case, they call it the belt speed. All right, how fast is that belt going linearly? All right, so when we have its radius, which is half of its diameter, that's what we see here, multiplied by its rotational speed in radians per, whether it's seconds or minutes, then what we're going to do is we multiply those two together and we get that pitch line speed. Many times for a belt, it's going to be given in feet per minute. That's just a very common, units that we work with. Okay, so you're probably going to see that come up in our example problems. And then here is where they mention the maximum power, the transfer of power happens between 4,000 and 5,000 feet per minute on pitch line speed. So you want to always check that, because then you can kind of target that that range right there and know that you've got good a good range there for your speed, and it's not going to be too fast or too slow. So let's look at our first example to put to work some of these concepts and equations that we've looked at. So let's take a peek at page 306, and we're gonna see the complete problem statement here. So and this is just below where we were just at on page 306, it says we have a belt drive. It's used to transmit power from an electric motor to a compressor for a refrigerated truck. The compressor must still operate when the truck is parked and the engine is not running. The 10 horsepower electric motor is rated at 3550 RPMs. So that's what's coming right off the motor. All right. The motor sheave diameter is 5 inches. So coming off that motor, they've got a sheave mounted already. And the compressor sheave, which is going to be on the actual truck or the machine, is going to be 7.5 inches. Determine the approximate linear belt size, the operating speed of the compressor, and the belt speed. Okay, so let's kind of look back underneath here. So I have here, you want to determine the belt size, the operating speed of that compressor, which is going to be our W2. We'll kind of identify each of these. And what I want you to do is just take that, for instance, and just first start off with these 3 questions. You want to answer these 3, and I'll give you a minute to kind of, look at the problem statement. What I want you to look at is, first of all, what do you already know? What's the given information that you have? And then as you look at what you need to calculate, what are the equations that you have to solve this problem? And then what do you think the steps are going to be? Now you can peek at the example. There aren't a whole lot of steps here. So if you wanted to peek, that's totally fine. But I challenge you to not at least attempt to kind of go through and kind of critically think about, how I would approach this problem, because this is how, problems are going to present themselves when you're out in industry. Okay. So go ahead and answer those 3 questions. I'm going to give you a minute, and then we'll look at this together. Okay. And then also try to line up the variables with the 1s and the 2s, where 1s are your driver, so the motor, and then the 2s will be your driven, which is going to be the compressor. Okay. So hopefully you had time to kind of, line some things up here. So first of all, as we look here, what do we know? When they're giving us some of the details, how would we, identify what 10 horsepower is? Yeah, we would that's a known value, right? Yeah, so it's going to be rated at, so your motor is equal to 10 horsepower, right? 10 horsepower. And then as we look here, it's rated at 3,500 RPM or 3,550 RPMs. What is that variable line up with anything that we've been talking about? Yeah, it does. It does, Eric. Don't go like this, like this. What does it line up with? A W, right? It's a rotational speed. Now, if we know that 1s are equal to driver and a 2 is equal to driven, okay, so this one is always your faster, And this one's going to be your slower, right? Would this be a W1 or a W2? It's going to be a W1, right? The motor is what's driving this compressor. Yeah. So we're going to say is equal to 3550 RPMs. Okay. Now it also lets us know that the sheave diameter is 5 inches. What variable lines up with that? Yes, so lowercase d, which is the pitch diameter of the driver, because it's going to be on the motor, is going to be equal to 5 inches. Good. And always make sure that you put your units along with this as well. Then it says that the compressor sheave is 7.5 inches. What would we call that? D2, right? So this is motor, right? And this is compressor. So the problem didn't say the pitch diameter for the sheave on the motor is, but you got to kind of, you know, see what they're giving you and line things up here. Okay. Good. Now they want us to determine the industrial belt size, and it's always good to add that too. So we want to find belt size, right? So I always say like equal to question mark. We also want to know what the operating speed of the compressor is. Operating speed of the compressor. What variable would that be?
Before we get too far, I sent the question in the chat, but
sorry.
I mean, basically, is the driven always or the driver always faster? Is that only based on which one's faster? Or is it based off the knowledge of like one side is the motor, one side is the compressor or fan or whatever?
Yeah, it is the motor, and this as a designer, you will know. So there are some assumptions that we have to come to basically because of problem descriptions that we have. But let's say out in industry, you would know where the driver is coming from. It can be where you actually are speeding up an application. So for instance, if you had the motor on the larger one, but you wanted to actually speed up it from what the motor was running, you could run this in the opposite direction and put a smaller sheave on your driven, and then you would be actually going faster. Okay, that doesn't happen very often. The most common, and I really want to say in the 90 percentile, most often you are going to be running these where coming off of the motor will be your faster, which will be your drive. That's where things are coming in, or an engine, for instance, and then it'll be going to some sort of a machine. Does that make sense? So we're setting it up that way.
Yeah, okay. I just want to make sure I saw faster and slower, and I didn't want to make the assumption that
most
always
often,
was the case. Because
yeah.
Okay.
And like I said, in the applications we're going to be doing here, yes, but you may run across one in the world that they don't happen often, but you can put these opposite. Just like on a gear drive, we always say it's a speed reducer and a torque increaser is the most common application, but it can switch. Absolutely can switch. Okay. So we're trying to find our belt size. So the operating speed for the compressor, what variable would we line up with that? Operating speed of the compressor. We know that the pitch diameter of the sheave on the compressor is 7.5 inches. But what would the operating speed of the compressor be? That would be W2. W2. We want to know what is the RPM of that compressor going to be operating at. Okay. And then lastly, belt speed. Belt speed. What variable goes along with belt speed? Yes. And we could, it's going to be V. Up in the top, they called it VB. So the pitch line speed, if you would, of that belt. So yeah. So V, the lowercase v. This is the straight line velocity component of something that's rotating. How fast is that? So these are the three things that we want to come up with. So knowing that this is what we need to find, now we want to kind of devise our plan of what we have available to us. Okay, so we have a couple of equations that we identified, and we're gonna scooch back here. Let's go over here. And they start first on page 304, and they go to page, well, 306 for the next couple pages here. So let's create a little equation sheet. All right, I always think it's nice to kind of get these all in a place where we want and need them. So this is going to be belt kinematic equations. Okay, so the first thing we want to do is this is going to be center distance range. Okay, and that's going to be D2. Then it's going to be, has to be less than your center distance. So the center distance is in the middle here. So it has to be greater than whatever your larger sheave is, but it has to be less than 3 times D1 plus D2 once we determine that. Okay, so this is a range, not an equation. It's going to be something that we're going to check. Okay. The next equation we're going to be interested in is going to be the belt length. Okay, so I'll let you, I don't know if I can do this up and down here, but this is going to be belt length. And capital L, it's going to be equal to, I got to write it off on the side here. It's this equation right here. 2 times the center distance plus pi divided by 2, D2 plus D1 plus and then the next one is going to be center distance. C. Okay. And that's going to be the equation we see here. And then your B would be equal to 4 times the length. So you want to write down this equation too. Minus 2 pi. And all that B does is it shortens up the equation for us so that it doesn't get so long. It takes those values of B, you calculate B first, and then you put it into the equation in those 2 spots. If we wouldn't, then you'd be squaring those values and the equation gets like really super long. Okay. Say that again. Mhm. All right. And then the next ones that we have to check are going to be the angle of wrap. Okay. So you'll notice these two equations down here. The first one is going to be, zoom in. The first one is going to be for theta 1. And if we look over here, theta 1 is going to be the angle that we get on our driver. Theta 2 is going to be the angle that we get on the driven, okay? Very similar equations. One's an adder, one's a subtractor, okay? But you're going to want to have these available too. And they're most often, it says angle of contact though, most often it's referred to as angle of wrap. Okay. Or what is the wrap angle? Then there's just two more. We're going to want to write down up at the top of page 305, the velocity ratio equation here. So we can use, this looks familiar to us, velocity ratio between two, or a set of shivs is going to be W1 over W2, but it's also equal to the radius of 2 to 1, and then the diameter of 2 to 1. And then here it's important to note, because we've done it a couple times, your ones are going to be equal to your faster, or your also known as the driver. And your twos are going to be the slower or driven. And then one last equation that we're going to find that we're going to need is going to be this pitch line speed. And this is referred to most often as the belt speed. And that's the straight line velocity component using R and W. So if you're on, for instance, the driver or the number 1, it has to be the radius number 1 with the W1. This is a mistake. This should be W1. These have to be on the same. And that's because this is just this expanded. And then this would be a W2 with the 2. So as we have our equations here, kind of all in one place, and we look at the problem that we're trying to determine, okay? We want to find our belt size, okay? We need to find that W2, the angular velocity of the compressor, and then also the straight line velocity or the belt speed. Okay. So as we look over here, where do we want to start? Why don't we start first with our belt size? Our belt size actually comes off of a table. So number 1 is going to be belt size. And we are going to look to either table or figure, I forget. It's going to be this one right here. Figure 11.4. Okay. And for our problem, it's saying that our motor has 100 horsepower and it's going at 3550 RPM. So as you look at this chart, what do you think? What size belt lines up there? A 3V, right? You would go 10, right? Until we see 3,500, and it's about there. So it's going to be right up in here is where they meet. So it is going to be a 3V. Okay, so that's going to be the answer to the belt size, right? That's going to be a 3V. That's where it lands on that chart. So our next one is going to be our W2. Okay, W2. So if we want to find W2, do we have any equations here that have W2 in it? Yeah, we have the velocity ratio, right? And it makes sense because we do want to find, okay, how fast is that going? So we know that the velocity ratio is going to be equal to W1 over W2, but it's also equal to, and we're working with diameter, so I'm presume that we're going to be using these D2s and D1s. So as we look here, how do we want to set this up? So we want to find out what is W2, right? And we know what D1 and D2 are. So if we know this, and we know that, and we know this, I heard ratio. How would we want to set this up? Right, exactly. So in variable form first, okay, so we'll say step number 2 here. We're going to find W2, right? So we know that W1 over W2 is equal to D2 over D1. And we know D2, 7.5. We know D1 is 5. We know W1 is 3550. We need to solve for W2, right? So we're going to have to rearrange. I always like to rearrange before I stick numbers in, okay? So go ahead and rearrange your equation to solve for W2 by itself, okay? You get W1 times D1 divided by D2. Okay, if so, then you're ready to plug your values in. So go ahead and do that. What did you get for W2? Mm-hmm. And it's RPMs, right? So this would be your answer for W2. Okay, so we've got 2 of them done. The last one we have is going to be that I'm going to call it pitch line speed, right? And it is. It's along that pitch diameter, if you would, of our pulleys and our belt. So it can be called that, but it's it's what we refer to in belt industry as belt speed. How fast is that belt going? Okay, so step number 3 is going to be belt speed, right? VB is equal to, right? So we go back to our equations. Is there an equation that has VB in it? Yeah, right. All the way at the bottom here, this one, right? Okay, now something to note about this, and it's probably something we want to add here, is that our W's cannot be in RPM in this, just like they couldn't be when we did our gear stuff. So our W's here have to be in radians per minute second, whatever we want them to be in now. And this is where you want to, think a little bit. As I said earlier, the most common units for belt speed are feet per minute. Okay, feet per minute. Okay, so if I want to calculate, if I know that my equation is going to be BB is going to be equal to R times W, and I know my W has to be in radians per, if I want this to be in feet per minute in the end, do you see how I would want to keep this in radians per minute? If that makes sense. Now, I also need to line up my radius and the rotational speed of the sheave that radius is on. So for instance, I need radius of 1 and W of 1, or radius of 2 and W of 2. All right. Since W1 was a given value and I ended up calculating for W2, I'm going to stick with the ones. All right. Just in case I hit a wrong calculator number or something like that, I want to kind of, keep to given information if possible. So go ahead and calculate your pitch line speed here. This is just like the gear stuff that we did. Trying to sneak it in here. I didn't want to turn the page over. I maybe should have. Yeah, like I said earlier, the most popular units for belt speed are going to be feet per minute. Feet per minute. So you should get 4,647 feet per minute. Is that what you guys got? Okay. So that's the linear speed. So if we look at, for instance, this belt arrangement, and I'm not sure if it's horizontal or vertical. Okay, we'll go something like this. So it's going like this, right? Okay. And if I go off of, and I call this my radius, so this looks like a link, right? This is number 1, this is number 2, and this would be, for instance, if this is, they're not telling us if it's going clockwise or counterclockwise, but if it's going counterclockwise, this would be my pitch line speed, my velocity of, if you would, point B, which is the belt speed as well. And that's going to be whatever my number is in feet per minute. Okay, it's the straight line velocity component of the rotational speed along the edge or the pitch diameter of that sheave. Okay, so really just like what we looked at, 4 gears, pitch line speed. Okay. So how did we do if we compare back to our example? We go to our final answer here, 4647. Look at that. 4647 feet per minute is equal to, sorry, mine got a little squished in here. Huh, I did. I didn't want to turn the page over. I thought I got a little bit of room here. But yeah. So did that make sense how we approach that? Sometimes they jump in the examples and they just start going, right? I think it's important too, because you're gonna be doing that process when you do your homework. You're gonna be like, okay, what do I have? What do I need to find? What are my equations? And how am I gonna approach this? Okay. All right, let's do another problem like this. All right, let's go straight to example 2. Okay, example 2. This one goes a little bit further. This is going to be a belt drive is required to reduce the speed of an electric motor for a grinding wheel. And the picture, and I like that they have the illustration here, is on the next page. So here is our motor with the shiv. This is going to be our driver. Okay, our driver. And then this is going to be driven. Okay, driven. And coming off the motor here, we know that our motor has 50 horsepower and it's rotating at 1725 RPM. Okay. And our grinding wheel, the desired, it says desired, it doesn't say absolute, but it says the desired wheel speed of that grinder is going to be 600 RPMs. Okay. And I'm going to put these little kind of not really equal, they're kind of the little wavy equals approximately. Okay, 600 RPMs. And what they want us to do in this problem is they want us to determine an appropriate belt size, find a suitable shiv diameters of stock pulleys, and then they tell us from table 11.1, which we saw earlier, and then also select a suitable belt length from table 11.2 and calculate the corresponding center distance. Okay. All right. So this one's a little bit longer. You'll kind of notice there are more steps. All right. So, but we want to approach it that very same way. We want to first decide. And if you go back to my PowerPoint and we move to the next one, really that very same thing. Number one, what do we know? What's our given information? All right. What do we need to find and what are our equations that we need to do? And maybe you don't have to list the steps, but at least get some direction. So go ahead and do that like we did on our last one. Line up some of our variables in the problem statement. Line up what the variables are going to be for what we're needing to find. And then, kind of identify some equations here that we're going to target in order to find the information. You don't have to solve it yet. Just kind of, plot a course. Yes, Eric. I thought you didn't write it down. They're also in your book too, It is also recorded. Yes, I think so. Let me check. I think I hit record. I did. It's still recording. I gotta look at my problem statement here. Just the bottom, Eric? I don't know if you still need it. It's also on, just so you know, it's also on page 304 in the book. Here, C is equal to. B is just a shortened, see, all they did was instead of putting all this business up in here, B isn't really a variable except you want to calculate it first and it's going to go up here and it's going to go there. That's all. So you're going to come up with a number and then put it in there. No. Well, what they could do is they could have like this ginormous equation otherwise. So they broke that part out and then it becomes part of the equation. Yeah. Okay. There's lots of typos in this book. I try to catch them as I go along. I have a couple versions of my book, whether they're at home or here. And sometimes I'm like, oh, shoot. Yeah. Yeah. Is it for the belt speed? Yeah.
Yes, on the table.
And this book is good. The first one was.
The last one they had, the last chapter they had they call it like table 10.7 a reference thing, and it was supposed to be 10.6.
Yeah, yeah.
Whatever.
Yeah, sometimes you have to be like, I know it. I think the copyright on this particular book is like 2012, so they haven't done one in a while. It's probably time. But it's like the third one. They did like 3 of them in a row. It didn't take long, I remember, because I like the book. It's just, yeah, there's a lot of mistakes. All right. So let's kind of start going through this. So what you have is, what's given is, you know that your motor, which is the driver, is rated at 50 horsepower and it rotates at 1720 RPM or 1725 RPM. Then your grinding wheel, which is going to be the driven machine, they want you to be at approximately 600 RPMs. Okay. And then in that process, they want us to kind of pick out the entire drive. They want us to determine the belt size, what are the diameters of the pulleys that you're looking at, what is going to be the length of the belt, and then also what is the center distance once we know our belt and our diameters. Okay. Now, one of the things in this problem as we kind of go through, we're going to find that they randomly pick out of the air a center distance. Many times in a design like this, you will know what your center distance is, or what at least a range is that you're going to be working within. And that's what kind of makes this a little like, how did they get? But they randomly picked a number. Okay, so when we get there, we'll identify that. But many times in real life, you will have a physical distance that you'll be trying to target for what your center distance needs to be. Okay. So belt size, we're going to look at figure 111. So we're going to go back to, or I'm sorry, 11. Oh, 11.4. I thought it was 11. Oh, it's table 11.1. So figure 11.4. We're going to use this to determine our appropriate belt size. So in our problem, it said 50 horsepower, 1725 RPM. What size belt do you think we are going to be targeting? Yeah, so I've got a 50, right, coming up here. My 1750 is there. So right around here, a 5V would be appropriate. Yep, so I'm going to be looking at a 5V belt, okay? A 5V belt. Now, that's going to become important when we start looking at our diameters of our sheave, because on table 11.2, we then have to be in the 5V, whoopsie, 11.1, they look the same. We have to be in the 5V column for the available shiv sizes, okay? So that's why we need to know first, what is our belt size for, or what is our belt like size that we're looking at? And then that's gonna help us to determine, okay, what are the shivs that we're gonna be able to pick from then? Because we need to pick off of this list, all right? So that's what we're gonna look at next, is gonna be the diameters 1 and 2. Okay, now for diameters 1 and 2, we know that we have to stick to standard size V-belts or V-belt shivs, right? But we also need to kind of figure out, okay, where are we at? All right. So we know that our pitch line speed optimally will be between 4,000 and 5,000 feet per minute, right? Feet per minute. And we also know that from our equation sheet, okay, we look here, we know that pitch line speed, small b, belt speed, is equal to d1 over 2, which would be the radius, times w1, right? Or our angular velocity of that same pulley or shiv, okay? So we can pick a number within this range for our pitch line speed. We also know from our problem statement that we're going at 1725 RPMs, but we would have to convert it down here into radians per, right? Minute or second, whatever we want to do. So we know that. So then we could solve for D1 here. Do you see that? Okay. So go ahead and rearrange this equation to solve for D1 first, and then we'll plug and we'll figure out our values. So just double checking my algebra. Did you guys get 2 times and then VB over W2? Yeah. I'm sorry, W1. Thank you. I said W2. I meant 2 times over VB over W1. So now we can put our values in here. Now, in the example problem, this is the range that we need to that's optimal for transmitting your horsepower and RPMs efficiently. Okay. So what we're going to do is, in the example, they pick 4,500 just to kind of target the middle of the road here. So they're going to go 4,500 and their value is in feet per minute. Okay. Feet per minute. Oh, I know. Why am I saying the right thing? I think I'm a little, I don't know. My brain isn't working with my hands today. So 4,500 feet per minute. So just the middle of the road here. And that's what they did just to start the process. Divided by W1. Now remember, this W1, that's angular velocity. It has to be in radians per. Now, notice that we have minutes here. So we're going to leave this in when we're going to go from revolutions per minute to just radians per minute. That way those units will cancel. So go ahead and get your W1 into radians per minute. You get 10,838 radians per minute. Okay. So we're going to plug that in underneath here. little bit more room. And then I'm gonna put a parentheses around this and I'm gonna multiply this by 2 because it's 2 times once I do that work. So my minutes cancel out and I'm gonna be left with feet. Feet divided by radians is feet, right? So go ahead and calculate your D1. But we need hours in inches, right? Now we have to convert 2 inches. .96 inches. Okay, any questions so far? So 9.96 inches, right? Is our estimated diameter based on using 4,500 as our pitch line speed. Okay, 4,500 feet per minute. Now, we're going to take this value and we are going to go to table 1-1. And we're going to find what is the closest number here. Okay. You didn't. What'd you get?
I got 0.41.
Did you multiply by 2?
No. Didn't.
Yep. Yeah, don't forget to multiply by 2. Because that would be, yeah, that's the radius. So once we have our 9.96, we're going to take that number and we're going to go over to our chart. Okay. And you'll notice they have a 9.7, but we're going to go up to 10.2. That's what the book does. They go to 10.2. So I'm going to just kind of follow what they're doing. You could go in either direction, quite honestly. All right. You're close there because this is just an estimate. And remember, we estimated it based on, we started in the middle of this 4,000 to 5,000 range, just like that's where we're starting, right? We didn't have that as a given, but it's a guideline for where it's going to be optimal. Okay. So what the book does is they pick for their D1, okay, from table 11.1, right? Table 11.1, they pick D1 equal to 10.2 inches. Okay, so the diameter of our driver sheave is 10.2 inches. Okay, so now that we have that, we can figure out what this is going to be, right? D2. Now, how can we figure that out? Well, we know that we want our speed to reduce to about approximately 600 RPMs, right? Okay. So if we expand out our velocity ratio, we know W2, we know W1, we know D1, we need to find this time D2. You see that? So we're going to set these two equal to these two and solve for our D2. Okay. Let's do step number 2. So we just expanded out that velocity ratio and we took the driver divided by driven speeds is equal to the driven diameter divided by the driver diameter. So we know 3 of the 4 here. So D2 is our only unknown. So we're going to multiply D1 up on the other side. And now we're going to take our value. So we had 10.2 inches is what we picked for D1 on the previous step. And then we're going to multiply that by. Now, in this case, we can go back to the RPMs, okay? Because this is just a ratio and those RPMs are going to cancel top to bottom. It's just a ratio here. We don't have to have these in radians per. So we know that our W1 from the problem statement was 1725 RPMs. And our W2, they said approximately 600 RPMs, right? RPMs cancel, and I'm going to end, and I'm going to say equal to D2. So I want to just double check before I even do any calculating. Are the units that are left over appropriate for a diameter? They are, right? Inches. So we should be good. So calculate out what, if we would go from 1725 to exactly 600, what would the pitch diameter of our driven machine have to be? Is that what you got? 29.33 inches. Okay, so now we go back to what are the available diameters of shivs? We go on our chart here. You're going to notice that the largest one that they have is 27.9. As a designer, I also don't like to be on the edge. I never like to be on the edge. I always like to be kind of in the middle of my chart. Now, they go ahead in the book and they continue to design. Okay, they say, oh, we're going to go with 27.9. Okay, and so instead of using 29.33, they use 27.9. And what ends up happening is 27.9 inches is going to be our D2. So this is what they end up going with. Okay. So then we have to check what is the actual rotational speed of our grinding wheel now, right? Because it's going to be affected because we base this one on 600 RPM. Well, now if this is going to be the new diameter, what is this? Okay. So we go back and we check that. So we want to know what is D2 actual. Okay. What is the actual RPM of number 2? If we're going to use this 27.9 in combination with the 10.10. So we redo this. We say, okay, W1 divided by W2 is going to be equal to D2 divided by D1. Now we have the two actuals. So we want to solve this again for W2 to find out what is it now that we have picked them. So you got to rearrange this equation. You're going to multiply this up. This comes down and then that goes up. So our W2 is going to be equal to W1 times D1 divided by D2 equal to 1725 RPMs, right? That's off of our motor. We know that D1 is 10.2 inches in there. Inches. Okay. Divided by 27.9 inches. So inches cancel top to bottom. RPM is left over for a W2. That's good. So my W2, now this is actual. Okay. Is 630.65 RPMs. There's two strikes against this design. They continue to go forward. They don't go back and they don't change anything. There's two things that I feel are a problem with this design. What do you think those two things are? First one is the 27.9. I'm at the limit of those pulleys. I don't like being there. I just don't. I've always been a little bit more conservative designer because I've seen designs fall apart if you push that envelope. Okay. I would not want to be there. All right. So that's one issue that I have with this. What's the other issue? There's another one. The rotational speed. I don't think 630 is approximately 600. I would want to see us be in between, maybe plus or minus 5 RPMs. But to me, you as a designer make that decision. I would go back and reiterate this. Okay? For those two reasons. Number one, you don't want to be on the edge of a, you know, standard sizes. And additionally, this is not to me approximately 6. This is plus 30. That's a lot. Okay? So that's what we're going to do. We're going to go back through this process and we're going to find a better number. Okay? A better pair. And there is a better pair. There is a better pair. So what could we do? Let's like retrace our steps. We chose our first diameter based on what? 4,500. Okay. We need this to get smaller. Which direction do we have to go in to get this smaller? So if we're at 4,500, which was the middle, do we go closer to 4,000 or do we go closer to 5,000 in order to get this first diameter to be smaller? I don't know. Which one do you think? If I want this number right here to get smaller, do I want my top number to be bigger or smaller? It's going to be divided by the same thing. Okay, so do that. Okay, go ahead and do that. Say, and I wouldn't even write it out just yet. Go ahead and do it. So 5,000 divided by 10,838, and then multiply that by 2. And then multiply that by 12, right? Did your diameter get smaller or larger? Yeah, you gotta, yeah. So you wanna take 5,000 divided by 10,838, multiply by 2, and then multiply by 12. And just kind of see, where am I at? Am I bigger or smaller than 9.96? I'm bigger, right? It's not the direction I want to go in. Let's go in the opposite direction. Let's put 4,000 up top here. Let's put 4,000 up there and see what we get. That's a guideline. They didn't come up with it. It was in the book. It's on the PowerPoint and it's at the very top of page 306. So right here it says belt transfer is the maximum power at speeds of 4,000 to 5,000 feet per minute. So it's like they're giving us that guideline. Mhm. Correct. Yep. Yep. So what do you get when you make this, for instance, 4,000? What happens to your diameter down here? It got smaller, right? So let's rework this to use those numbers. All right, let's start at 4,000 and see where we end up this time. Okay. And this is called the design process. The design process, when you pick your first numbers, remember, we're just kind of starting out to see where we land. And in this case, we weren't happy with where we landed. Kelly wasn't happy with where we landed. It's not good design to be at those edges, okay? So now what we're doing is we're saying, okay, we're still gonna operate within this range, but let's start inside of the pulleys further. So we're gonna redo step number 2, and we're gonna say VB, our belt speed, small b, VB, it's gonna be equal to, we're gonna say 4,000. And that's gonna be feet per minute. So now we're gonna use this equation right here that we rearranged. D1 is equal to 2 times VB divided by W1. Okay, and we'll start there. Now remember, in this equation, this W has to be in radians per minute. And we did calculate the radians per minute before, so you don't have to rewrite that calculation. We know it to be 10,838 radians per minute. So we come out to 0.7381 feet. But then we say 1 foot is equal to 12 inches. We convert this to 8.86 inches, right? For your D1. So this got smaller. We were at 9.96 last time. Now we're at 8.86. So we're going to be about an inch smaller. So when we go up here, you're going to notice that we were here before. We can go all the way up to 8.9, right? 8.9. So that's what we're going to do. We're going to say, all right, D1 is going to be equal to 8.9, and that's from table 11.1. Okay, so we're going to pick that one. So then we're going to redo step number 3. And if we turn over our previous page, we want to find our D2 this time. So we rearrange this equation, right? So D2 was equal to D1 times W1 over W2. Okay. W1 we knew to be 1725. And then this is where we're estimating, okay, we're going to use that 600 and see what is our D2 going to be equal to now, and try to find something on the chart close to that. So we now know that our D1 is 8.9 inches. And we're going to multiply that by 1725 RPMs divided by 600 RPMs, because we're targeting that. RPMs cancel. D2 Did you come up with 25.59 this time? Okay, cool. So now we're going to take this number and we're going to go to, and we're going to find, okay, 25.59. Well, we're closer to 27.9. 25.59 doesn't quite get us. You could try 25.1. Or we could use the 27.9, either one. Okay, but now we're not way over it. Last time we were at 29 and we were using the 27. So why don't we try the 25.1 and see how that goes? Okay, because then that's not at the edge of this. So we're going to just say D2 is going to be 25.1 inches. Okay. So now we have to redo this equation to find W2. So if we know that W1 over W2 is equal to D2 over D1, we want to solve for W2. Is that what you ended up getting, Eric? You got that? I saw somebody. Okay. Anybody else get that? Should have. Now, compared to 630, this is closer to 600. We could try the 27.9. Do you want to try it? Jacob says, nope, I'm good. Not hard. What do we do? Do this very same equation, but put 27.9 in there, right? Was it 27.9? Yeah, do it. Do the same thing. Just go real quick on your calculator. 1725 times 8.9 divided by 27.9. Let's see, did I do that right? 1725, 8.9 times 27.9 divide. What do you end up with? 550, yeah. So what was that? I know, but I mean, you wouldn't have felt good without trying it. But that's how you play around with it. Does that make sense to everybody? You kind of saw, you know, it doesn't have to be like, how do you guys feel better about this design? I do. I feel like we're not on the edge with our diameter. I know we're only one in, but we're not on the edge, and we're much closer to what our approximate 600 was. Okay. Yes.
Now, what is the suggested number we should be within?
There wasn't, and that's the thing. You as a designer would get to make that decision. And I guess they felt, all right, 630, that's approximately 600. I don't think so. I ran the numbers earlier. I knew we could get closer. I'm like, I don't like it. I don't like it. But you as a designer, when you're out in industry, you'll have a better feel for what is acceptable or not. Okay. And then sometimes even in our problems, it'll give you plus or minus or within, you know, plus or minus 5 or 10 RPMs you want to be. Okay. So we are going to proceed with the numbers we have on the second try. All right. So our numbers are going to now slightly differ from what the book is going to do, but we have a better design. All right. Okay. So, so as we get back to their process here, we'll kind of see where we're at. I got to get to the beginning. So we now have, let's kind of look at, we've got our belt size figured out. We did our D1, our D2. Now we're going to be looking at the length of the belt and the center distance. Okay, the length of the belt and the center distance. So the length of the belt, So you'll notice down here, length of the belt. This is going to be this equation right here. You'll also find it on page 304. Page 304 right there. It's 11.1 is that first equation. Okay. Now, we don't know what our center distance is yet, right? So if we look at this equation, we really can't find the length of the belt until we know what our center distance is. So we need to kind of determine, okay, what is our center distance? We weren't given it in this problem. All right. Unfortunately. Most often you will, as I said earlier, you'll know some sort of a range that you need to get your center distance within, but they didn't give us that. So we're going to use this and we're going to find what the range is, and then we're going to pick a number out. Okay. All right. So let's figure out what our range is. What is the smallest number and what is the largest number? Now, the smallest number you can see here is going to be, I got to get my sheets here. So this is, I just got to look at where I'm at on my steps. I think this is step number 5. I was on 4, right? Now we'll do step number 5. Okay. And we want to find now the range for C, which is our center distance. Okay. And so we know that it's going to be D2 is going to be the smallest number. So we know the smallest number that it can actually be, or it has to be a little bit larger than the diameter of our driven sprocket or our driven shiv. And our C has to be here, and then our C has to be less than 3 times D1 plus D2. Okay, so we know this number is going to be 25.1, right? We went with the 25.1. And that's inches. Okay. And then this number over here, so our C has to be 3 times our D1. Our D1, 8.9 inches, and our D2 is 25.1. 8.9. And that's inches and inches. So that number is get 102 inches. Okay, so this is our range. Okay, we have to be between here and here. And the book just picked 72. That was it. All right. So what's our number? What do you want it to be? 72. Jacob says we're going with 72. All right. So this is going to be our, if you, I don't know, what do we want to call it? C. It's not the actual, it's the C trial, TR. 72 inches. Okay. So this is what we're going to kind of use for a little bit here. All right. And now we're going to use that number to find the length of our belts. Okay. So here, we're going to use that center distance in here, and we're going to find the length of the belt first, but then we have to compare to our chart to see what's the closest none. Okay. So go ahead and plug your C trial in and your D1s and your D2s to calculate for the length of your belt. Okay. What was that? Probably not. We get to do it again. Two. Oh, I didn't write my equation in variable form. I just broke my rule. Damn it. Sorry, I have to do it. I can't. I can't. 2 times C. Dang it. It's almost done. Make sure you always write your equation in variable form first. And then put your numbers in. 2 times 72 inches plus pi divided by 2. 25.1. I don't know why that one doesn't stick in my head. So fun. Do it again, but this is what I got. I don't know if you got 201.4. Try again. I only did it once through, so I can't say for sure. I got it twice. Did anybody else get 201.42? Jacob did? Okay, I'm sure it is. So make sure usually it's probably over here. Don't forget to square that top part, okay? And that's what I did. I actually started at that end and did that first. And then actually worked backwards. So 201.42. Now, once we have this, now we can look to table 11.2. Okay, and in this section right here where we have 5V belts, we want to find something close to 201, and look at that. There's a 200. There's a 200. Okay, we were expecting we weren't going to get it exactly the same, right? But now we've got a 200. All right, which is pretty darn close to 201. So you want to go ahead now and calculate your center distance. Now, you don't need to go back into this equation, all right? And that's where these two help us out, okay? So instead of having to go back in here and try to solve for C and find all that, this is rearranged for us. But you're going to have to solve for B first. So knowing our new length is 200, we're going to use the two diameters. We're going to get the value for B, and then you're going to plug in B for each one there and then finish out the equation. Does that make sense to everybody? Okay. So use in this equation first, you have to do B first. L is going to be 200 because that's going to be the length that we pick. And then now we need to just calculate that center distance. Okay. And those equations are found here on page 304. It's these two equations right there. 11.2 and 11.3. So 11.3 is where you're starting with the new length. And then once you get your B, you're going to plug it back up into that equation. Correct. Table 11.2. So right there. And you're going to be in the 5V section. Six. Just to the bottom here. That's a pretty heavy duty equation. Yeah. But I did it twice. It's a good number. So you should end up with, and I know it takes a little bit of time to go through this, and I suggest taking it step by step by step. But you should get 72.85 inches for the center distance, and that makes sense. Remember, we picked 72. We determined the length on 72, and we had 201 as the length of the belt. Then we picked a 200 length belt. Now remember that 200 was to go over both of those pulleys and maintain about a 72 center distance. So when we picked the 200, it was just an inch less than what we had anticipated or what we had the trial length as. So we went to the 200 length belt, and our actual center distance then is going to be 72.85 inches. Did anybody get all the way through yet and get the very same number? Make sure you can, because you're going to be doing this on your own for a problem or two. And remember, we changed the numbers from the book, so they're not going to match the book. So you want to make sure that you can get this number here now. Jacob got it? Okay, good. Okay. So as we look back at the original problem and what it wanted us to do, we have accomplished it, right? We have our length now is 200 inches, and that's the total length of the entire, closed off length of the belt, and 72 point, what did we say? 85 inches. Okay. And then we have our diameter one was 8.9 inches from our table, and then 25.1 inches for our D2. and our belt size was a 5V. Right, so we did each one of these parts here. So it's a pretty involved process, but that's what they call the design process. You designed an entire drive, picking out pulleys, specifying the length of a belt, determining the center distances, so that you can now incorporate this and specify it out and purchase what you need and plunk it into your design, okay? And we were given, if you would, a pretty generic opening statement. The only thing that we ended up picking was our center distance. Like that wasn't given to us, right? So we picked 72, and then that's how we kind of went forward. And so did the book, but we used 2 different pulley diameters than what they did. Okay. So any questions at all? I'll just kind of put this back up at the very end if you need to reference those numbers there. But otherwise, I think we're going to stop there right now for belts. We'll take a break and then we'll be back with chains. So I'll pause the recording. Okay, now we are ready to look at chains. Now, the nice thing about chains is that we're gonna see kind of a ditto on a lot of stuff. Okay, so what we'll do is we'll kind of go through the basics here. We'll work an example, and then we'll start looking at the homework that you have available that you get to do to reinforce this. What? A ditto, like you can say ditto, like, oh, it's the same as. So the kinematics of chains is going to be the same as the kinematics that we saw for belts. and then there's going to be some similarities to gears as well that we're going to find out. All right, so as we look at the function of chain drives here, you're going to notice that it's the very same function that we had for both gears and belt drives. So to transmit rotational motion and torque from one shaft to another smoothly, quietly, and inexpensively. All right. So chain drives are kind of like a combination between belts and gears. All right. So they're going to be low cost, very readily available, but we're not going to have any slippage. So as with belts, especially when we had the V-belt types, we relied on friction to keep the belt in contact with the sheave. But now we're going to have teeth that are going to come up between our chain. And now this is going to kind of give us that non-slipping type of a drive. Okay. So with that, it provides a more efficient power transmission. Okay. We still get the flexibility of the center distance. So we have that ability to kind of go back and forth with that. Okay. And then a more efficient, it's going to be more efficient at low speeds than what belts are. All right. There's also a little maintenance, just like it was for the belt drives. And then we do have a longer life on than our belts, just because now we're made out of metal. Okay. And so it's gonna be able to last longer as long as we maintain them properly. So different types of chain. There's roller chain, there's multi-strand chain, there's offset sidebar roller chain, and then there's an inverted tooth silent chain. So on page 308, if we look at figure 11.8, it's an example of each one of these types of chains. So here's roller chain. This is going to be similar to, or almost, it's really identical to the type of chain that would be on like a bicycle. Okay. You'll notice here we have multi-stranded roller chain. So it's same type of, arrangement as the roller chain, but now we've got them, if you would, ganged together in multiple rows. And what we gain there is going to be transmitting more horsepower and torque through that chain. Okay. The next one we have is, this is called an offset bar or sidebar roller chain. So just a different arrangement. And then lastly, we have this silent chain, and this is that inverted tooth type. Okay. Now, one of the biggest advantages of roller chain is that these links and rollers come apart. So especially when we're in an automation type of an atmosphere, we can run these along conveyors and we can add different things to actually move and push items along to get to another location. Okay, so that's why they're very advantageous, especially in automation or like packaging equipment. We see a lot of chains because then we can customize those to make them fit what we want them to do. I did a lot of that when I was out in industry and worked in high high-speed packaging equipment, and we would take chains apart all the time, make up pieces that would go in there, have bars that would push product along, and it really, it worked really, really well, and very inexpensive and very readily available. Okay, so you'll notice that they're used a lot out in industry. Over here. So let's talk about chain pitch. So roller chain is going to be classified by its pitch. All right. So in figure 11.9, up at the top of page 309 is going to be a picture. And you'll notice that the dimension for pitch there is going to be between where we have, the two holes in the actual side plate of our roller chain. Now, the size is going to refer to the pitch in 1/80th of an inch increments. So a number 20 chain divided by 80 means that the pitch is going to be 1.5 inches between the two holes on that side link. So if I go back underneath here and we look at the pitch here, that distance right there corresponds to whatever the number of roller chain is divided by 80. That's a distance then. So when we look at different size roller chains in the chart down here below, you're going to notice that at the bottom, we start with a smaller number. So here's 25, 35, 40, and so on, all the way up to 240 are the standard sizes for industrial chain. Now, to get what the actual pitch is in inches, we would divide a number like 25 by 80, and that's going to then be the distance from hole to hole on that side link. So take 25 and divide by 80. What do you get? .3125. What is that size in fractional inches? Do you guys know? What size is it? Just over 1/8 of an inch. Yeah. What size exactly is that? 5/16 of an inch. Correct. Thank you, Jacob. You were thinking I'm divided by 80. No. Yeah. So it's 5/16 of an inch. Exactly. So now if you take, for instance, 60, number 60 chain. So you would call that number 25 chain. So then that distance on that pitch is 0.3125 or 5/16. So kind of small chain, right? Kind of small chain. If we take 60 and we divide that by 80, what do you get? You get 3/4 of an inch, right? 0.75 is going to be that distance. So I just got bigger. So the chain number, we would always divide by 80 to get the actual physical distance. Okay. So number 80 chain is going to be what? 80 divided by 80 is 1 inch. So the larger the number, the larger the chain. And we also then start to realize that as we look at, as we look at this design horsepower, this is going up, up, up as well. So as you can imagine, the chain gets larger and chunkier. It can push more torque, rotational speed, and horsepower through it without having any problems. Okay, without having any problems. Okay. Now, we can have multi-strand chains. So if we're looking at one chain and we're like, I really wish I could put 2 of these together so that I could get more out of it, right? Unfortunately, they do not provide a direct multiple. So if my one strand provides 10 horsepower that I can run through there, 2 of them is not going to be 20, okay? There are factors that are going to be available, and they're not quite a multiple of the number of strands. So here at the top of page 310, you can look at the number of roller chain strands. So if I have 2, 3, 4, 5, whatever the numbers are here, the factor then is actually going to be listed below. So if I have 2 strands, I don't get 2 times the horsepower out of it. I get 1.7. So if you wanted to figure out what the power was per chain, you would take the total transmitted horsepower that you need and divide it by the actual factor up here. Okay. And then you would know how much you're going to get out of each one. Okay, so keep that in mind. If you need more chains, you don't just say, oh, I want 3 of them. That means I'm gonna get 3 times the horsepower and strength. That's not how it works. Yes,
That's the one where there's side by side, right?
correct. It's gonna be like these guys right here when I have multiple chains. Yep, yep. But when it's one, it's whatever you read off the chart as the horsepower. Mhm. Now, the sprocket, so chain and sprocket. So when we looked at belt drives have their belts and they have their corresponding, either a sheave or a pulley, you call it, okay? But when we're talking about chain drives, it's their chain and their sprocket, okay? So the sprocket is gonna be the toothed wheel that then is gonna go up in between each one of those chain spaces, and it's gonna be what pulls it around and joins with the other sprocket. So the teeth on a sprocket are designed with geometry that's going to conform to the chain, pin, and link. So they're designed to fit up in between. So you have to match up the sprocket tooth formation in the correct number of chain to match with the chain number. So you can't take a number 80 chain and put it on a number 60 sprocket. Okay, so those have to match up together. So you always pair those together. So if we look at figure 1111 and 1112, we'll see these together. So on page 310, here is a sprocket. Okay, so you'll notice that the teeth coming up are going to be what fits in between those spaces in the chain. And then it's going to have an elongated hub on it, because most often when we mount it to our shaft, we need a little bit more contact with that shaft to rotationally be able to push that through. And there's going to be a key that's going to be in there that's actually going to do the transmitting. And we'll talk about that in machine elements, but kind of a simplistic view here, the hub elongates, you know, how far we can have contact with our shaft to get that transmitted. Now, over on the right-hand side, we're now seeing a driver sprocket and a driven sprocket. Driver is going to be all like we talked about earlier with the belts. We're going to have this as being the higher speed sprocket in the design. And then the driven is going to be the lower speed. Okay, the lower speed. Now, as this pulls around, you're going to notice that in this case, the driver is going in a counterclockwise direction. So kind of the opposite of what we saw earlier with the belt drive. So since it's going to be going counterclockwise, that means it's pulling this side along, and then your slack side is going to be on the bottom. Okay, that's actually the preferred arrangement. Why do you think so? To make sure that your slack side is on the bottom. For a chain drive, oh, go ahead, Eric. Exactly. So when we look at this arrangement of a chain itself is going to be heavier than a belt, right? Okay. And especially, I mean, when you kind of look side by side for the same application, even though the belt is going to be getting bigger and chunkier, rubber and a little bit of, you know, maybe wire on the inside is not going to be as heavy as the steel that the chains are going to be made out of, or the metal. So this is going to want to hang down. Okay. And like Eric said, we don't want that hanging in the middle here of the design. Okay. We want that tight side on the top, and we keep the slack on the bottom so that gravity can help us with that. Okay. So that's the best, you know, arrangement. Now, does that mean that you can't do it? Not meaning you can't, but this is the preferred arrangement that we work with. Okay, so try to make that happen, you know, in your design as you do your arrangements. Now, pitch diameter. It's another familiar term that we've heard it when we talked about gears. We heard it when we talked about belts, and now we're going to hear it again when we talk about sprockets. So pitch diameter is going to be the diameter across the middle of the sprocket. Okay, the middle of the sprocket. So if we go back to that very same illustration that we just looked at, it's right in the middle there. It's where we get contact with our chain. Okay, it's that effective diameter, just like it has been for the other two elements. And pitch diameter is going to be, you know, how we size our sprockets. Now, the sprocket is going to be, we figure out the pitch diameter based on, let's see. Oh yeah, here it is. I didn't see the N. I was like, wait a second, that's not the right equation. We calculate the pitch diameter here based on the top here, this is going to be the chain pitch. Okay, so this is going to be the numerical value in inches. So for instance, if it's an number 80 chain, that's going to be 1 inch on top. So it has to be in inch increments. It's not going to be the number. And then underneath, you're going to divide by sine times 180 divided by capital N. What does capital N sound like? Remember when we had capital N for gears? What was that for? The number of teeth. Same thing here. Okay, so that's going to be then how you calculate your pitch diameter based on the chain pitch in inches, and then you're going to be using your divided by your number of teeth at the bottom here. Okay, now center distance is going to be figured out, kind of giving us that same ratio again. So here we're going to take 30 times whatever the chain pitch is, and that has to, the center distance has to be greater than that, but less than 50 times the chain pitches, okay, in inches. Chain length. Now it's not, maybe not the exact same equation, but it looks kind of familiar on how it's set up here, okay? And then center distance is going to be the last equation that we see here. Once we pick our actual length, here's the center distance based on the number of teeth on each one of the sprockets and the length of our chain. And then lastly, we're always interested in how much wrap do we have on each one of our sprockets. So this is going to be on the driver and this is going to be on the driven. Okay, we can calculate what that is as well. Now, over on the right-hand side, I know I'm getting a little bit ahead of my, my PowerPoint, but we'll catch ourselves up as long as we're here. You'll notice that equation 1115 looks pretty darn familiar to us, doesn't it? Looks exactly the same as the one that we had for gears, because now it added back in the number of teeth this time. So same kinematics here. That's why it's kind of nice to learn the gears first, right? Kind of go through that business. Now we learned about the belts. They go a little bit faster because it all sounds familiar. And then chains now, again, are another reapplication of that. And then lastly, you'll notice that this time we have chain speed, just like we had belt speed before. This is the pitch line speed, like in gears, but now we're going to use the diameter of the sprocket and we're going to multiply by, or I'm sorry, divide by 2 to get the radius, but then we're going to multiply by however fast that sprocket is rotating. And remember, we have to keep that in radians per whatever increment of time. Now, in the case of chain speed, that'll also most often be in feet per minute. Okay, feet per minute. Now you'll see here that there's a couple different types of speeds. So there's low, medium or moderate, and then high speed. So anything that's below 650 feet per minute, that's considered low speed. And we can run a chain that way, that's no problem, but we have to provide lubrication. And in this case, we would manually lubricate it, meaning every so often we would just kind of, put a little lubrication on there and we would let it run for a while and then do the same thing when we noticed that it needed it. If we get into the moderate and the high speed, now we've got to start incorporating some bath lubrication or oil stream lubrication in the design that we have. Now, we aren't going that far here in kinematics, but as we identify what our pitch line speed is, we do want to keep that in mind with the, going forward with the design. So you'll notice that in the examples that they have, or the example that we do in class here and in your homework, it's going to ask you what is the lubrication type. And that's what they're referring to. Like, where did your pitch line speed come out to be? And depending on where it fell here as a slow, moderate, or a high speed, you would then identify the type of lubrication that would be suggested. Okay. And before we look at our example problem, I just want to show you, because I don't know, I skipped over it for some reason. I was glancing. We have this chart right here. This is chart or table 11.5, commercially available single strand sprockets. So when we specify sprockets based on the chain size, right? They are not going to make the sprocket in like infinite number of teeth, okay, for a sprocket. So if we know that we want a number 60 sprocket because that's the chain that we're using, you're going to notice that they have 8 through 60 in single tooth increments. So you can pick any one of those numbers and that's how many teeth are going to be on the outside of your sprocket. But then after 60, notice that they no longer do every single one of the teeth, okay? So you have to know, if you would, by your manufacturer, what is going to be, you know, the number of teeth that's available. And that could vary by manufacturer, but these are the, you know, if you would, those standard ones that they have to abide by. If they're going to say, I'm making number 80 roller chain, they have to do all of these and, or in addition to, you know, something that they want to offer in their product line. Okay. So that's why we'll be able to use this information, but you'd always want to check with your vendor's catalog to be sure that you're, you know, getting what they offer. Okay. So with that, let's take a peek at an example. Well, before we do that, let's make sure we have all of the stuff. So we talked about the geometry, the center distance, the length, the center angle of contact. Okay, so we hit all those equations. We talked about velocity ratio and chain speed. So now we're ready to do our last example. Okay, so let's look at the problem statement at the bottom of page 311, and then we'll kind of come back over here and decide how we're going to tackle this. Okay, so problem 311 says that we have a single strand roller chain drive connects a 10 horsepower engine to a lawn waste chipper shredder as shown. And you're going to find that it's on the following page right here. Okay, so this is our faster speed. This is our lower speed. This is the chipper, you know, business that's going on. So this is our driver. This is the driven. All right. And it's telling us that the engine is operating at 1200 RPM and the shredding teeth should rotate at 240 RPM. All right. The drive sprocket has 18 teeth. Determine the approximate pitch of the chain, the number of teeth on the driven sprocket, and the pitch diameters of both sprockets and chain speed. Also indicate the number of links in a suitable chain and specify the required center distance. All right, so let's actually, from the problem statement, before we go too far, let's kind of go back over here. We read the complete statement. We need to determine what they have here that we just read over. So let's kind of write down, just like we did on the last problems, take a minute to reread the problem. What do we know? What's the given information? What are we trying to find? And then, you know, how are we going to kind of, you know, go forward with what equations are we going to target? Okay, so go ahead. And I'll put this back up in case you don't have your book. And kind of write down the start of our problem here. All right, so as we look here, given in our problem, they're telling us that we're gonna go with a single strand roller chain, okay? So they've already picked that out. The engine that is driving this chipper is a 10 horsepower engine that is rotating at 1200 RPM. So that's gonna be our W1, okay? Any of the ones are gonna be that engine or that driver, and then any of the twos are gonna be the chipper or the driven machine, if you would, okay? The chipper, which is the driven machine, they want to rotate at 240 RPMs. So this is going to be our W2, our W2. And that's, you know, we want to get as close to that as possible. And then they're telling us that the number of teeth on our sprocket on our engine, which is our driver, is going to be an N1 is equal to 18 teeth. Okay. So what we want to find and determine is going to be an appropriate pitch for this application. So that's going to be that P. That's going to be the number of the roller chain we're going to be picking out. We want to find out, okay, how many teeth need to be on that driven sprocket for whatever the pitch that we have. So we have to make sure that we can get a sprocket that size. Then we want to we want to determine the pitch diameters of each one of the sprockets. Then we need to know what the pitch line speed is of that chain, or what they call the chain speed. So that's going to be the VC. And then this last part, links and the center distance. So links is when we determine, you know, what our center distance is, how many links would we pull off like a roll of chain? We would literally count an even number of links. We'll talk about that. Now these two, they didn't give us a center distance. So you'll find that in the problem, we're going to check that range again, and we're just going to they're going to pick a center distance out of the air, if you would. Okay. Just like that one's good because it's within the range. But again, you would in the real world have something you'd be going off of. Okay. That you needed to accomplish. All right. So where do we start? What do you think? Probably start with that pitch of that chain, right, Jacob? Yeah. So we're gonna determine what the appropriate pitch. Did you say that, or was it Eric who said that? Did Eric? Oh, I thought it was you. Sorry. So yeah, let's figure out what that pitch number that we're gonna have, and to do that, on page 309 we have this chart right here, figure 1110, and the number that's going up here is going to be the number of the pitch. Okay. And then over here, this is going to be the design horsepower. And if you look at the top of this column, we're going to go down the single strand column. So you got to look in your book because these are pretty small. Now our horsepower is going to be 10. So we want to find where 10 is. 10 is right there, kind of in the middle. And then the speed at the bottom here of our small sprocket needs to be 1200. So we're going to go up to about there. And you'll notice that they meet right here, okay? So we're between and really close to the edge of 50 and 40. So this would be your call, all right? Now, if I was doing this, guess what I would pick? I'd probably pick 50, all right? But 40 is not a terrible number, but let's see I forget what the book does. Thinking belts. What do they, oh, see? I don't agree with them. They're picking a 40, but we'll go with the 40. Not happy with the 40. Huh? Do we want to go 50? I guess I don't know if it really matters. We'll just be off on our numbers then. Are you guys okay? We'll go rogue. We'll create our own path.
For the assignment, though, we should stick with them.
No, you're the designer. What would you do? Even if it was on the assignment, what would you do? What would you do? It's like The Price is Right, is it? Do you feel good being close to the line on design? I don't.
Well, you're either close to the line on one side or close to the line on the other side.
Which side would you want to be on? The bigger chain or the smaller chain? Do you want to be at the highest value on the smaller chain or the lowest value on the chunkier, bigger chain? Chain is cheap. It really is. It really is. Well, you know what though? You bring up a great point. Maybe there's other places that you're using this very same chain on a machine or in your company's product line, and maybe they more readily get 40s in. yeah, go with the 40 then. If you feel like we definitely have more of that available, it's, you know, better price, it's lighter. There, I mean, there's a lot of variations that go into that, right? So those might be other parts of the equation. The other thing that they're not doing here, I will tell you, when we get into machine design and when we do chain drives, they're calling this, you'll notice, design horsepower. We're only going off of the horsepower coming off of our engine. All right. There's more to design horsepower than this. All right. And we will be probably going up on our scale here to a design horsepower that's higher, that's taller than the horsepower that's coming off of the engine. And we're going to end up going with a larger number anyway. Okay. So I always think it's good to err on, you know, being conservative, but so they're going with 40. We will go with their numbers. We'll stick with the book for right now. I don't know if I'm going to feel good about it, but we'll go with it. They have all the information. So notice that they selected the number 40 chain. So now what we want to do is we want to determine, and we'll put this up here. We're going to go with 40, number 40 chain. And then we'll convert that over when we need to a little bit later on. So we have that one done. So that was step number 1, if you would. Step number 2 now is going to be determining the number of teeth on our sprocket that's going to be on our chipper. Okay. Now to do that, we are going to go through that velocity equation or that velocity ratio equation. So going back over here, do you guys want to make an equation sheet for chains, or do you feel good about just using the book? We could take time to make an equation sheet. Do you like having them in one place?
Yeah.
Yeah. Then let's take a moment and let's kind of gather all the equations, and then we can just go back to one sheet. I know we've been doing that as we go along, so we might as well be consistent. So what I'm going to do is I'm going to pause our recording for a little bit while we create it, and we're going to be gathering the equations that we, you know, have here in our chain section, and they're all found on page 311. So we will be back. Okay, so now that we have all of our equations organized on one sheet, and they all come from page 311. Okay, so those were the equations. It's nice and handy, all in one spot, getting our pitch diameters related. The velocity ratios here are familiar, but it really comes down to different equations for the lengths and the center distances based on now working with chains instead of belts or gears. Okay. So, so let's kind of put that aside and relook at where we're going. So we have the number of teeth, or I'm sorry, the number of the chain we chose is going to be number 40, going along with what the book had suggested. And now we're ready to look at what is the number of teeth on our driven sprocket, which is attached to the chipper. Now, what we're given in our problem is the number of teeth that are on the driver sprocket, which is 18. And we also know that we have, if you would, the W1 and the W2 from 1200 RPMs to 240. So using the velocity equation relationship or velocity ratio relationship here, we have W1 and W2. We have the number of teeth in number 1, so we need to calculate for number 2. So we can set those two equal to each other and solve for N2. So that's what we'll do. So we are going to take W1 divided by W2. We're going to set that equal to N2 divided by N1. Okay. So now solving for N2, this is going to be equal to, we're going to take N1 and we're going to multiply it up. So we're going to have W1 times N1 divided by W2. So solving for N2 here, our W1 was 1200 RPMs. Our N1, 18 teeth. And our W2, we want it to be 240, okay? 240 RPMs. This means that the RPMs cancel out, so we don't have to do our converting here because this is just our ratio. And now our N2 calculated gonna be 90 teeth, okay? Now, we need to find out, is that a standard number of teeth for number 40 sprocket chain? So we're gonna look on table 11.5. We're gonna find number 40 chain. We're gonna go over. Oh, look at that. We've got a 90. So what that means is we don't have to recalculate or try to pick something closer. All right. And what it also means is since we have a rotational speed of 240 and we came up with exactly 90, we don't have to recalculate it, and it's going to be 1200 to 240, which is perfect. All right. Doesn't always happen that way, as we saw in our belt drive. Okay, cool. So we've got, we can cross out our question mark, and we say, oh, we got 90 teeth on N2. Now we want to figure out what the pitch diameters are of our driver and our driven. And from our equation, the pitch diameters of a sprocket are going to be the pitch, and this is going to be in inches, divided by sine times 180, divided by the number of teeth for that particular sprocket. So if you want to find out the D1, you have to use the number of teeth in number 1. Okay. So for this one, so for step number 3, then we know that D1 is going to be equal to P divided by sine of 180 divided by N1, right? Okay. Now, our pitch, we need to determine what the pitch is in inches. We know the number, but to get it in pitches, or to get it in inches, sorry, the pitch in inches, the pitch is going to be equal to the number divided by 80. So we're going to take 40 divided by 80, and we're going to get 0.5 inches. Okay. So this is the number then that we're going to put up there. Okay. So now we're going to put our numbers in place. So this is going to be 0.5 inches divided by sine here, times 180 divided by the number of teeth was 18 teeth. So D1 is going to be equal to, and this will be in inches, 0.5. Double check we can do that correctly. All right, yeah. So I'll get 2.88 inches. And then we're going to do that very same thing for D2 using that same pitch. So D2 is going to be equal to 0.50 inches divided by sine times 180 divided by, this one is 90 teeth. So D2 inches. Oh, it's dimensionless. So you would go 180 divided by 90 and then just hit the sine function. It's just it's the decimal equivalent of 180 divided by 90, and then you hit sine. So it's 0.0349. I don't know how your calculator works. So that's why when you compare the answers here, do it in one or the other. It doesn't matter. So then you'll know how to do it on your calculator. Does that make sense? Yeah. So you should get 14.33 for the second the second pitch diameter? Yeah, yes, which matches what the book has here. So we're right here. So these are our two pitch diameters. All right. Any questions so far? So now we are ready. So let's kind of go back to what we already have done. So now we know our pitch diameters of numbers 1 and 2. So this is going to be 2.88 inches. And this one's going to be 14.33 inches. Now we need our chain speed. Okay, chain speed. So looking back at our equation sheet, our chain speed is right here. All right. So now we just pick which sprocket we want to look at. And the best thing to do usually is to stick with the one that's mostly defined, which is going to be our W1, because it gave us the diameter in the problem, and it also gave us the 1200 RPM. Now we can't use 1200 RPM here, and we know we want to get to feet per minute. So we're going to actually convert so that we get into radians per minute. Okay. Before we use that equation. So step number 4, chain speed. So VC is equal to R1 W1. And this is going to be the radius of the pitch diameter. That's what R1 is. But we need to get this in radians per minute. So we know W1 is equal to 1200 revolutions per minute. 1 revolution is equal to 2 pi radians. Cancel that out. Our W1 should come out to be 7,539.6 radians per minute. And keeping it in per minute because we're going to be converting this to feet per minute. So it's one less level that we have to do. So now we're going to use that number and we're going to put it up there. So VC R1 is going to be the pitch diameter for number 1 divided by 2. So 2.88 divided by 2. So 1.44 inches times 7,539.6 radians per minute. So our VC $10,857 inches per minute. Right? And to convert that to feet per minute, I know that there's 12 inches in 1 foot. Inches go on the bottom. So I'm in feet per minute. So my VC should be 904 feet. You can just put FPM, feet per minute. Oh. Did I do something wrong? I got 904 too, but they got 1300. Let me double check. They have 1200 RPMs as 10,838 radians per minute. Let me double check that math. Yeah, we're right. We're right. So we're gonna, this number, this 10,838, that was from the previous problem. We were using that. So I wonder if that got crossed over for some reason. So this should be 7539.6 positive. And then this should be 904, right? Did you guys get 904, everybody? All the way along, yeah. So that is not it. Okay. All right, how are we doing? So now let's go back to our problem. We just did pitch line speed, 904, right? feet per minute. Two more. Okay. We need to determine the length of our chain that's going to be going around our sprockets in links. And we need to also determine what a center distance is going to be. So what they've done down here in step number 5, they set up that like range. So they took 30 times the pitches. The center distance has to be greater than that. And then the center distance has to be less than 50 times the pitches. Now this is the pitches in inches. So as we know, a number 40 chain is 0.5 on its pitches in inches, right? So when we look at 30 times 0.5, the center distance can be in between 15 inches and it can go up to 50 times 0.5 up to 25. Okay, so they're picking a center distance between those two numbers. Okay, and at the top over here, did they pick it? It looks like they picked, oh, up here, the mid value is 20 inches. Now, I cannot emphasize again, we don't just randomly pick center distances like that. You're going to have probably a physical, dimension that you're like, I have to get it in between here. Okay. So, so you would know more specifically what that center distance would be, but this is a good place to start in this case. So they picked 20. All right. So now what we want to do is we want to determine when we get chain, we pick it off of a roll. So if you ever gone to the hardware store and you had to get chain, there's a roll of chain and you literally pick 1, 2, 3, 4, 5, and you just count your links. You count your links. So we want to know how many links do we need to have a center distance of 20 inches and make it around my two sprockets and still maintain about that 20-inch distance. Okay. But I have to have like exact number of links. So you'll notice here that they go through and I don't think it's worth going through it twice. So I'm going to point at what they're doing here. Okay. So the number of links here you're going to notice is going to be based on the center distance that we have. So this center distance is the 20 inches. The pitches is the 0.5. So it's the pitches in inches. And then you're going to take the number of teeth in your driven and your driver, and you're going to plug these in. So the math isn't hard. And what they end up with is 137.28 links. Okay. Now, you as the designer then need to determine, am I going to go 137? Am I going to do 136? Am I going to do 138? Okay. Because you have to put it on an even increment or an integer number, because I can't have a 0.28 of a link, right? I'm going to count my links, just like I can't have 0.28 of a tooth. All right. So they picked 138 links. So now what they're going to do is they redo the calculation to solve for what is my actual center distance when I have this many links, because it's not going to be exactly 20 anymore, because now I am going to be getting 138 links instead of 137.28. And they plug that in. So the number of links here, capital L, is the number of links, and that's going to be the 138 that they settled on. And then 138 settled on again here, and then the other numbers that we have in there. So the actual center distance is going to be 20.187. Okay. These two are plug and chug. As you kind of look at that, do you see, I see where the numbers are all coming from at this point. I just don't think it's worth spending our time just chugging them in. Agreed. But what I will encourage you to do is, if you have problems with yours, make sure you can get these numbers so that you know how to plug it into your calculator. Okay. So that it comes out. Any questions on that? And that's the last two parts of what they're asking us to do here. Okay. All right. So that brings us to the end of chain drives. All right. So now let's kind of shift gears and we will look at the homework. Okay. And what I'll also do is kind of go back to our PowerPoint and make sure what you're ready to do. Yeah, now you can begin your assigned homework problems related to chains and belt drives. Okay. So I am going to stop sharing for right now, because then I'll just create another video on just the homework. Okay, so that's a little bit separate. So I'm going to stop recording and we'll be back.